Okay, I hope you're able to see me and able to listen me. So yeah, let's start this live session. So actually, I just went to an article and let me just show you. So I hope you are able to see. So like if you go to this website app.daily.dev, it is a very good website if you want to just learn about different like if you want to get basically the tech articles and all those things. So it is a very good website. I would recommend you highly to visit this and actually like whenever I joined the this tech corporate world, I made this habit to read 1 to 2 docs every day. Eventually I get to know from one of my senior that he's actually good, very good at this coding stuff, and from him only I got to know that if you are reading like this type of articles, it is eventually going to help you in your future. So yeah, I just went to this articles, and it is created by byte go, and previously also I have seen a lot of articles from them like this. So if you want to get these kind of articles from them, you can subscribe to their newsletter. So for now, let's go to this article. So this telling about like how Uber serves over 150 million read per seconds from integrated cache. Like even I have not read this article before, but let's read this together and understand what is happening behind the scenes. Okay, I think it's some ad. Okay, okay. The detail in the post has been derived from the details shared online by the Uber engineering team. So engineering team. Okay, so the writer has mentioned that all this information has been derived from Uber engineering team, like the articles which they have shared. So yeah, when you open the Uber app to request a ride, check your trip history or view driver detail. You expect instant result. Yeah, behind that seamless experience lies a sophisticated cache system. Per cache front server, okay, over 150 million database read per second, maintaining strong consistency guarantee. This article will break down how system challenges they faced and the innovation solution they developed. Trip history and view driver detail. Expect instant result. Okay. Every time a user interact with the Uber platform, the system need to fetch data like user profile, trip details, driver location, and price information reading directly from the database for every request and reduce latency and create a massive load on the database server. We have millions of users making billions of requests per day. Traditional database cannot keep up. So yeah, that's true. If you are just relying on database and if you're not using cache, then it's a big problem because making this read heavy operations on database, like if you are putting a lot of requests to like read data, that is like a problem. So ideally, yeah, in between they use cache, and even in our systems we are using cache. We are basically using redis over there. So yeah, basically you can configure a redis container in your kubernetes, and you can put all those you can put like the important most like the request where the user make the most of the request to that particular resource, so you can put them in the cache. And what will happen is like also you can set an expiry to that. So first your application will check in the cache. If it is there, then okay, it's a hit. Otherwise it's a miss. Then it will try to query it from the database and will get the right information from there. So yeah, so all this by storing frequent access data in a faster source and so running the database every time the application First, check the cache. If the data exists here, cache hit, it returns immediately. If not, the cache miss. The system queries the database and store this result in cache for a future. So, just to tell you, like, even this kind of like similar kind of thing, uh, you have coded while you are studying about the operating system. So we have did that part. Maybe you have done that. I'm not sure. So normal cache pattern, okay, it's like this. So there's a service which okay, they have not put that thing. Okay, so here read the data from cache. So it will make the a request to cache. If it is a hit, it will get the data. Otherwise, what it will do, it will query the database and then it will put this data into the cache. So it's a simple flow how it is. Okay, Uber use Redis. Okay, Uber also use Redis. uh, I guess I'm not sure, but ma'am, what kind of cache are available? Uh, Popular cache tools, maybe we can say. Okay, yeah, Memcache, and there are various like Redis is the most popular one, but I know that Memcached is one among them, and yeah, there are Aerospike, Apache Ignite. Okay, so the most popular one is the Redis, often used as database cache and is broken. A high performance distributed memory object caching system designed for simplicity. It's highly efficient for speeding up dynamic databases driven. Okay, no SQL database that functional well as a cache. Okay, Aerospike is not fully a cache, it's a NoSQL database which is used as a cache. Okay, Apache Ignite is an in memory computing platform that can act as a cache. Okay, okay. So you can basically say like a cache is kind of a database only, but it's like the like basically you can make this read operation very fast in that. So let's see the architecture. The architecture, three layers working together. Uber storage system called Dockstore consists of three main component. Okay, the query engine layer is stateless and handles all incoming requests from Uber service. The storage engine layer is where data actually lives. Okay, using MySQL database organized into multiple nodes. Okay, cache front is the caching logic implemented within the query engine layer, sitting between the application requests and the database. Okay, okay, okay. So let's just say this. But basically, it is telling that. Okay, so if suppose there's a microservice over here, so this is the query engine which makes most of the query, and here is the storage engine where we have the MySQL and other things. And yeah, these are some things streaming and streaming related things. I'm not sure. Maybe this is like a depiction of Kafka. I'm not sure. I'm really not sure. But here, like basically the thing is like if microservice, like it will query to the query engine that I want this thing, then it will check into the cache. If it is not there, then it will go to the database. It will basically go to the storage engine. So yeah, the read path. Whenever a read request comes in the cache front, first checks Redis. If the data exists in Redis, it returns immediately to the client. Uber achieve cache hit rate about 99% for many of the users. Okay, but achieve this line seems interesting. Uber achieve cache hit rate about 99.9% for many use cases. Meaning only a tiny fraction of requests need to touch that database. If this is true, it's like insane. Like, I'm not sure how they're like getting 99.9% hit. Maybe they, if it is so, then if it is like if they are doing it for user, so I'm just thinking like it will be like all the user data will almost be present on the cache side as well. So yeah, that is there. That data does not exist in Redis. Cache front fetch it from MySQL, which make complete sense. Write it to Redis and return the result to client. The system may handle partial cache miss as well. If, for example, if request asks for 10 rows and 7 exist in cache, it only fetches the missing 3 from the data. Oh, okay. This is something interesting. So, if suppose some 10 rows are requested and if 7 are present in the cache, so from for the database, like only 3 extra rows will be queried. Okay, the query engine, it will read from the cache. If not, go to database and will write to the cache. Write introduce significant complexity to any caching system. When data changes in the database, the cache copied to that data becomes stale. Serving stale data breaks application logic and create poor user experience. For example, imagining updating your destination in the Uber app, but the system keeps showing your old destination because it is reading from an old outdated cache entry. So yeah, actually this is a problem which I was thinking like how they handle it, because if there is some data which is like very frequently updated, and like even if we are reading it from cache, like then it's a problem. So like in that case, the data is old and I don't know how they handle it. Let's check. The challenge with refreshing the cache is determined with cache entry need to be invalidated when a write occurs. Uber support two type of write operation. Okay, I got it. So whenever there is a write operation to database, it will write it to cache as well. Okay. So refreshing the cache is determine which cache entry need to be occurs. Okay. Uber support two types of write operation and they require different approach. Point writes are straightforward. These are insert, update, or delete. Query whenever the exact row being modified are specified in the query itself. Okay. These are insert, update, or delete queries when the exact row being modified. The query itself, for example, updating a specific user profile by their user ID. It point writes your know exactly which cache entries to invalidate because the row key are part of the query. Okay, dates are far more complex. These updates or delete query when where claw that filtered based on the condition. For example, may I'm marking all trips longer than 60 minutes are completed because executing the query you do not know which row will match the condition, therefore cannot invalidate the cache entry because you do not know which one are affected. Uber initially could not invalidate the cache synchronized during write. They had to rely on other mechanism. Okay, the original solution Uber initially approach used a system called Flux, which implements change data capture MySQL binary logs, which record every changes made to the database. When I write commits, write it to the Bing log. This log sees which row changed, then invalidate or update the corresponding entry in the Redis. It's the diagram below. Mhm. Okay, so what I'm understanding from this thing is like how previously they used to do it is like whenever there's a read operation, so simply they will check in the cache if it is there. If it is not there, then it will query to the storage engine, and it will be okay. But whenever there's a write operation, so what it will do, it will write that row to the database, and also they have some tool called Flux. Basically, it reads the logs, binary log, bin logs of MySQL writes it to the bin log. Okay, MySQL write it to the bin log, and Flux tails this log, see which rows are changed, and then invalidate or update the corresponding entry in the Redis. So it will check those logs, and then accordingly it will update entries in the Redis. Flux operates asynchronously, meaning there is a delay between when data change in the database and when the delay is usually sub-second, but can stretch longer during system restart deployment. Okay, so the problem is like it's asynchronous, and it can take some time to update the cache, which is okay. Like, but like it's very less time. Uh, but although it can take a lot time if there's a restart or is there something other happening. So yeah, the asynchronous create consistency problem. If a user write data and immediately read it back, that might get old cache value because Flux has not yet proceed this invalidation. It read your own write consistency, which is functional in expectation. In most application, the system also relied on time to leave expiration. It's basically TTL. Uh, so how much time it should leave to leave expiring. Condition 5 minutes. Though this can be a gestation requirement. Expiration act as a backstop that even if invalidation fails, stale data eventually get removed. However, TTL based expiration alone is insufficient for many use case. Service owner wanted higher cache hit rates, which pushed them to increase TTL values. However, long TTL data may cache longer, but also increasing the window for. Okay, so basically, if I give you a summary, what is the problem is like they have this Flux which will read the logs, and based on that, it will update the items in the. But the problem is like it will take a little time to do that because uh, there's a short time after which it will start its processing and update the cache. But if in that time some user came and he's like okay, I just want to check that information, and but he will see the cache stale information which it does not want. So that is the problem again. For each entry there is a TTL, that time to leave. So if suppose someone has put 5 minutes, so that is again the case that if Flux has not updated it, and it will get that information like which is already stale, and it is going to remain for 5 minutes over there. So eventually database is also not queried. The again other problem is like if you want to achieve that much high rate of cache hit, so for that basically you have to increase the TTL, which is again causing other problems. Okay. So basically it is causing some consistency issue, and that's beyond TTL. Okay. The staleness beyond TTL. There was another stubble subtle consistency issue that was related to how stale cache data will actually become. Most engineering assume that if you set a TTL of 5 minutes, stale data will exist for almost 5 minutes. This assumption is incorrect. Okay, so even if we set the cache for 5 minutes, it won't stale in that time. It won't be removed in that time. This scenario, a row has returned to the database 1 year ago. Okay, has not been accessed since. Okay, some row has been returned to the database and it's not been accessed till now. Time t, which is today, a read request comes in. The cache does not have this row, so it fetched from the database and cached it. The cache entry now contain 1 year old data. Yeah. Moments later, a write request updates this row in the database. Flux attempts to invalidate the cache entry, but invalidation fails due to a temporary Redis issue. Now this cache still contain the 1 year old value while the database has the fresh value. For the next hour, assuming 1 hour TTL, every read request will return the 1 year old cache data. Okay. The world, the staleness is beyond bounded by the TTL duration. Even though TTL is only 1 hour, the application may be serving data that is actually 1 year old. Okay, of data. It only controls how long the cache entry lives, not how old the data inside it can be. Okay, the problem becomes more severe with longer TTLs. Service owner wanting higher cache hit rates, increasing TTL to would increase TTL to 24 hours or more. For invalidation fail, they would serve extremely outdated data for the. Okay, so in a case of like when it's like the write operation on Redis is failing, so like already we have a very old data which is like 1 year old, and we do not know, like TTL does not manage that okay this data is 1 year old or how much old it is. So that is again the problem, the breakthrough. Let's see what breakthrough they have made. The fundamental blocker for synchronous cache invalidation was not knowing which but condition update Uber made two critical changes. So this first they converted on delete to soft delete. They implemented strict monotonic timestamp. Okay, so made two critical change to the storage engine. Uber has made two critical change to the storage engine. First, they converted all delete to soft delete by setting a tombstone flag inside of remove instead of removing the row. Basically, they are not removing any row. They are just flagging it that it's been deleted. It's kind of soft delete. Basically, in the database, you have a column where you just put like a delete equals to true, that kind of thing. Second, they implemented strictly monotonic timestamps at microsecond precision, making each transaction uniquely identifiable. So basically, I guess they have changed the primary ID to like which has a very high precision. Okay, let's see how. I'm not sure how it will help, but let's see. This guarantees the system can now determine which rows were modified. When rows get updated, their timestamp column is set to transaction unique timestamp just before committing. The system execute a lightweight query to select all rows key modified within the transaction. Okay. Yeah, I'm just curious to know. Just I'm coming. I'm coming in a second. Actually, I just have to take water. So yeah, I'm just coming in a second. Hey, so yeah, I just take water now. Let's just read the full one. Okay. With this, currently the system can now determine which rows were modified. When rows get updated, their timestamp column is set to transaction unique timestamp. Just before committing, the system execute a lightweight query to select all rows he modified within the transaction timestamp window. This query is fast because the data is already cached in MySQL storage engine as index. The ability to track all modified row